Alright, so we will begin this lecture now. This is lecture number 4 in high performance scientific computing. So, in the previous lecture, we have started giving you a demo of a typical scientific computing exercise in the Python language, because that's the language we'll start with, given the ease of understanding the syntax and so on. And in the process, I'll also give you some understanding of the Python language in a couple of lectures. Right. We'll continue with that exercise that we had started, and we also in the process started to learn Git. Okay. So we had done a couple of, let's have a quick recap. So I talked about version control in Git last time, and I also gave you a short demo of GitHub, which is a repository management system, where we had set up a new repo. We did our first commit, and we also pushed our commit onto the GitHub website. So now you can in fact clone the repository on your local machines or the virtual machines, and get whatever changes we have done to the code. Okay. In fact, take it as a homework if you have not done it already, to clone the class website, and as and when we make changes to the repository, as like we will do it today, so you can keep pulling the changes. So I'll show you, give you a short demo as to how to do that. And we also learned some basic commands of Git, such as git status. Again, we'll use it today. So the git status is the command that we tend to use a lot to check the status of our repository, whether we have any new files to be committed, what is the status, and so on. We also did a git add, which was to add the file that we want to commit to the repository. And then once we have added the file that we want to commit, we committed that, because you can have multiple files that you are working on, but some of them are in work, and you only want to commit one or a few particular files. So you can do that. In fact, you have to add a certain number of files to be able to do a commit, and once we do a commit, that sort of freezes that commit or a version. Well, version is typically used for a different sense, but let's loosely call it a version, that we have a certain version committed, and if you want, you can revert to that version in the future. So there is like that changes are flagged with a certain commit ID, hash code that you can use to go back or check out the same commit that you had done in the past. And then once we have done the commit, we pushed the repository to GitHub, because commits are happening locally. Unless you push it to your GitHub, unless we pushed it to the GitHub project, then it will just stay on my local machine. So once I pushed it, whatever delta changes were there between the version I pulled, in case I had pulled it, and the version I had committed in the process, so all the commits done recently locally, they go back to the server. So now if you pull it, you will get the latest commits. And we briefly looked at the git log command, which is used to look at all the log of commits, and we did that on the terminal, Unix terminal. But if you want, you can also use some kind of a GUI software, but GUI in the backend is running those commands only. So I'll strongly recommend you to use the terminal version of the commands, because typically you tend to use clusters or supercomputers, which only allow you to interact with them over a terminal. And then we started solving a scientific computing exercise, which was to calculate the square root of a number. And the method we employed was to use the Newton's method to solve for the zeros or the roots of a polynomial s squared minus x equal to, well, the polynomial was s squared minus x, which is a function of s. So x is the number that you want to find the square root of. So the zeros of this polynomial s squared minus x will give you the square root. We are only looking for the positive one. So that's one way to find the square root of a number. Okay. So we did something, and we will continue from that point today. Any questions till now? Right, good. By the way, let's in fact do a quick demo of cloning the class repository. so that if you want today to do that, you can do it. So let me switch to the virtual machine. Some people had an issue with doing an apt-get, because we had set up proxies for the last year. So once we start the lab, I'll move around and help you with that. Or the easiest thing to do is you can download a fresh version of the virtual machine in the cloud link that was given in lecture 1, so that you don't have to worry about these things. Because still we had proxy enabled on the network at IT Mandi, but now it's proxyless access. So people proxy from last year, which prevents you from accessing internet through the virtual machine. Right. So this is the terminal. I hope people at the back can read the text. So what we will do is we'll pull the repository as it is. Let's have a look at the repo. Right, so let's Google the class repo. So we had set up this repository HPSC underscore 2024. So what we'll have to do is we'll have to go to this code here and then HTTPS, and I can copy this complete link, and then I can clone it with this. So let's go back to our repo. So I'll have to decide which folder I want to do it. So let's go to the desktop and I'll make a folder using mkdir, and then let's call it test underscore repo. I'm just doing this to demonstrate to you because I already have the repo at one place which I am pushing from. So I have two different folders, but this could be two different machines and so on. So let's do a git clone. So I'll write a git clone, and then I have to specify the path to the repo which we just saw. So this is the path to the repo. So https github.com/gbhotani/hpsc2024.git. So okay, so it's done. So now if I do an ls, I can see the repository HPSC 2024. Okay, so if I go into that, I can see that there's a codes folder. Sorry. So there is a codes folder, Python, and then my square root. And here I can see that my square root.py file that we had committed last time. And in fact, you can also do a git log, and you can see that this is actually indeed a git repository. Let's decrease the size of this window. Right, so we can see that it tells us that this commit was done by Gaurav on Wednesday, January 24 at 7:26 p.m. Okay, and it gives the commit message as well. And we can do a cat and look at the code here, which is this code. So that's the Python script we are done. We'll have to refine this because that's a very rudimentary script. So let's do that. and in the process, as I said, we learn how to do scientific computing step by step, and each version we'll keep committing in case we'll want to go back to the history of any of the versions. Right. I also wanted to demonstrate to you a couple of Unix commands. Let's clean up the prompt here. So I'll do a ps1 equals dollar space, so that avoids this long path that I had to see. So there's a command called history. I'm not sure if I demonstrated that to you. So if you type that in Unix, let's clear the screen first. So if I write history, it gives me the history of all the commands that I have typed, and also a number. So it has a numbering starting from 1 all the way on the top, and so on. So in case I want to repeat something from the history, what I can do is I can use an exclamation followed by the number. So let's say I would want to enable the course virtual environment, and this is the command I used in the history. So rather than copying pasting it, because this number in the history will still stay the same, sorry. So it's 291. So what I can do is I can simply write exclamation 291, and that runs this command, which was the 291st command in the history. I don't know how useful that is, but this is just one thing that you can use. Okay. Let's deactivate this because we don't need this virtual environment for now. Another thing you can do is you can do a reverse search. So if I do a control R, that says reverse interactive search, and here I can write, I vaguely remember that the command I want from the history has the word activate in it. So if I do activate, and then I don't want this deactivate command, so I can press control R again. So it basically toggles me through all the history commands which have the word activate in them, and once I am happy, I can just press enter, and that executes the command again. So control R is a very useful shortcut in Unix. You can also do something such as, for example, let's say we have the code here. So let's open this code using this command, or let's cat it. So cat mysquarero.py, and I see this. Now the last command in the history is this cat mysquarero.py, and the rightmost word in this is mysquarero.py. Now the next thing typically I would want to do is I would want to run it. So I would write Python followed by the code name. But if the code name is large with a lot of directory details and so on, I can what I can do is I can use this command, which is exclamation dollar. Well, let me show you what this exclamation dollar means. So if I do an echo, it basically just extracts the last most word in the previous command and uses that. So in case I want to do a Python followed by the same code that I just did a cat on, then I can simply write Python followed by exclamation dollar, and that will run this command Python mysquarero.py. Now we have an issue because Python is not installed in the base Unix here, but the point is that typically if you want to keep doing a cat, so what sometimes we do is we use the up arrow, we go to this cat, and then we delete the cat and write Python. So rather than doing that, you can simply do use this exclamation dollar shortcut, which extracts the last word out of the previous command. So these are just shortcuts that I'll use a lot during the course of these things. So I just thought I'll explain that. In case you want to run the previous command again, so you can do exclamation exclamation, that just repeats the previous command. in case you would, you're printing the output from a file, the latest version. So as the code is running in the background, it's putting new data into the file. So you'll want to read that. So if you want to keep doing that again and again, you can use exclamation, but I mean, it's actually much easier to use the up arrow and then press the enter command. Okay. Right. Another useful thing is the bash rc file, which many of you will tend to use, especially if you use the cluster. So bash rc file is available in the home as a hidden file. So let's go to home. Right now I am in this folder. So let's do a cd, and that simply takes me to my home folder. And here if I do an ls followed by dot bash and a star for anything that has comes after this dot bash, I see that I have 3 files. The rightmost one is .bash rc. Okay. So let's look into it. So let me do cat. Okay, so it's a long file. So what I'll do is I'll use an editor called Vim. Okay. So Vim is an editor which is quite useful, especially because it does some highlighting of the syntax. So if I do a Vim followed by this .bash rc. So I can use this sign now. So this opens my .bash rc file, which is available in the home. So here I see that it has lots of stuff in it. So what happens is whenever you start your terminal, then it loads this .bash rc file first. Okay, it sources the technical term. It sources this .bash rc file. So if you want, you can put stuff here. So for example, what I have done is at the bottom I have put an alias which says this word HPSC. If I type HPSC in the terminal, this will mean that I am doing a cd into this folder, and this is the folder where I have my repository. So I don't have to all the time, if I am in some home folder or somewhere else, I'll have to write the complete path, which takes a lot of time. So I can simply have an alias here which will help me get into that. And you can put many things here if you want. So just explore this file, and if you want to load it, it will load this file by default if you close and open the terminal again, or you can use the source command to open the load this bash rc file in the background. In fact, you can source from any file, but .bash rc file typically automatically gets sourced when you open a new terminal. So if I write HPSC here, that simply takes me to my folder where I have my HPSC repository. So you can set up these aliases that save you a lot of time in case you feel that you are doing something repetitively and that's wasting a lot of effort on your part. Any questions? By the way, in this bash rc file, let me show you another thing. Sorry, go to my home and do a vim on this. So if I go on the top, you see that there are these environment variables called hist size and hist file size. So hist size is the number of commands that your your terminal can store. If you do an up arrow, it will go through history, right? So the total number of commands. So by default, I think it's 500 or 1000. So I have increased that to 10,000 because I would want to maintain the history. And everything that you write once you close the terminal will stay in the history file. So the history file in my case has 20,000 lines it can store, and hist size, the history in the terminal, is 10,000. So if I open 2 different terminals, then they can each store 10,000 recent commands, and they'll all go into history file, which will have a total of 20,000. And once I go beyond that, it will rewrite the first one. So it will keep rolling over the previous commands. So it's good to have a large history size in case you would want to revisit some previous command. Okay, I can come out of this Vim editor using :q. So if you want to understand the commands of Vim, you will have to just Google about that. There are some basic ones that you will tend to use a lot, but there are many interesting things you can do in this editor. And the good thing is it's working on the terminal. So in case you are connected to some other computer through terminal, you can still edit files because Featherpad in this case uses a graphical interface which may not be available to you on a terminal. Okay, you can also use a nano editor which does the job. of basic editing in case you would want, and it gives you some commands like control X will come out of for exit. Saving if you want to, if I make a change, I try to exit, it will ask me that whether you want to save the recent changes or not. Okay. So Nano is also very useful in case you want to edit something on terminal. It's quite light and it's available by default. Right, so let's quickly jump into our HPSC folder. Right, and here what we were doing was we had committed our first version of the code, which looks like this, but to run it I need Python 3. So for that, what I'll do is I'll have to enable the virtual environment. So let's do a reverse search on okay. So I do a source on the virtual environment that's available on the desktop. So you can see that it says VENV, which means that this environment called VENV has now been enabled. And now if I type Python, well, which Python? Okay, so it gives us something. So Python is available now inside the virtual environment. So now, well, in fact, we were working on IPython, which is an interactive Python shell, which looks like this. So if you type IPython and press enter, it will open the IPython shell. Let's clear the screen, and to run the code, in fact, in this IPython shell, some basic Unix commands also work. So I can type pwd, it tells me the it prints the working directory. I can do an ls, it tells me the list of files available in this folder that I'm in. Okay. So you can do also use a cd and change the directory if you want, but I'm happy with my current directory. So if I want to run this my square root.py file, I can use this run command. So I can write run followed by my sqrt.py, and it will try to run the Python script, and you can see that it actually throws an error because there is some problem here. I think I just copied and did not try running it. It's looking for a Kmax which is not available. So let's edit that in a separate window. Let's use Nano for editing. So what I am doing is I have set the value of x. So if those who were not there last time, so what we are doing here is we are simply setting up a first guess for the value of s, which is going to store the value of square root of x. So x is 2 here, so we are trying to find the square root of 2, and we start with an initial guess of the square root equal to 1, and then we iterate again and again, but this time I'll have to set the value of Kmax. So let's say we are doing a total of 10 iterations, and then what I do is in each iteration I update the value of the square root s as the average of s and x by s, and we discussed that Newton's method gives us this formula. So let's save this. So I have saved this now. I'll go to my IPython shell again and let's run it, and this time it runs. It did not give me that error, but it did not print anything, and the reason is because I did not ask the script to print anything. Let's look at the script again. So the script simply is updating the value of s, but we are not printing that. Okay. So to print that I have to write print s here, and when I do that it will print the value of s, which is quite accurate in terms of it matches well with the square root of s. In fact, I can check, I can import the square root function from the math module. Sorry. Okay, so I have imported sqrt function from the math module and the math library, and then I can check if this is working. So I can write square root of 2, and this is what it is. So I can just take a difference of square root of 2 and s, and it is of the order of 10 to the minus 16. So that means our result is quite accurate in that sense. Is that clear? Right, so let's change the value of x. Let's play around with that. So let me change x to 9.0. Let's save it with control O, and then see if it works. So I'll again run my square root. In fact, I don't need to write .py. If I write my square root and press enter, it will look for a file called my square root.py and run it. So again, if I look at the value of s, it's 3.0. So square root of 9 is 3.0, so it's working well. So let's commit it now. I'm happy with this version now. So I will commit it. So let's go to the code, exit, and for that what I'll do is I'll look at git status first. So when I do a git status, this time it tells me that my square root.py has been modified with the red color. Okay. So it's telling me that this file is modified, and I may want to add. It actually tells me that you will have to use git add followed by the file name to update which file you want to commit. So in case if I do a git commit now with a message that corrected replaced kmax with 10 to resolve error. Okay, and if I press enter here, it says that no changes added to commit. Okay, so as an added safety feature or as a feature, I mean you have to add the file that you want to commit first. So for that I have to do a git add followed by the file name, which is my square root.py, and now if I press enter and do a git status again, so let's clear things first, and now you can see that it tells me that in a green color that this file changes to be committed, and it says my square root.py which has been modified. Okay, so now these changes are ready to be committed. So this time if I do a git commit minus m, which is minus m is for a message, replaced kmax with 10 to resolve error, this time it works. It says replaced this one file has been changed, 2 insertions, 2 deletions. So if I do a git status now, there is nothing to commit because I have already committed that file and there was only one file that was modified. Okay, you can do a git log and see that now we have 2 commits, one which has been done recently and one which was done last time. So you can always go back to any of these versions and recover them when needed. So I will show you in a bit of in some time, once we have a couple of commits, how to go from one commit to the other and so on. Is that clear? Right, so this code is very rudimentary. This does what we want, but this does not give us enough information that we can see on the screen in case you are trying to debug something. So let's modify this code a bit to make it a bit more richer in terms of content. This time I'll use the Vim editor for editing files. So what I'll do now is I want to get I want to see what is the value of s for each iteration. So, I would want to see how the value of s changes over the number of iterations, how it goes from s equal to 1.0, which was our first case, to the actual square root of x. So, for that I will print the value of s for each iteration. Okay. So, I am adding this print command inside the loop. So, I will say at iteration number k, the value of s is equal to. So, whatever I put in curly braces inside this big string will actually resolve from the variable. So, we have variable k and we also have a variable s. So, these are called f strings in Python 3. So, I have to add an f before I start the string. So, whenever you have an f string, this simply replaces the value of the variable inside curly braces with the actual value when it prints this on the screen. So, let us save this and run it again in the terminal. So, a tab also works in IPython shell. Let us clear this first. Okay, so this time I see the whole process. It tells me at iteration 0, which is before anything happens, the value of s was 1.0, that is the initial value. Then it becomes 5, then slowly it starts getting towards 3, and by the end of 6th iteration, it has converged to 3.0. Okay. Let us change it to 2.0 x and run it again. So, again this time I see that after the end of after the 5th iteration, the value of s does not change anymore. So, it is just repeating the thing still 10 iterations because I asked it to do that, but otherwise after a couple of iterations it stops changing the value of s. So, s has converged to the final value. Is that clear? And we can also because we are printing that before the iteration. So, once we come out of the loop, finally we can print the value again. So, let us run it again. Okay, so it tells me the value of in each iteration, and it also prints that finally at iteration, in fact this is iteration 10 or just let us say finally the value of s is equal to this, because see we are printing the value before the update. So, there is one more update that happens before it prints the value. So, it gives me the value at each iteration and then it says finally the value of s is equal to this. So, this is the value of s that you have. So, I am quite happy with this version now. So, let us do a quick git commit. So, let us check git status. It says again that mysqueryroot.py has been modified. So, we will have to add it. Let us say you had multiple files that you wanted to add. So, it is a lot of work to, let us say you had 10 files. So, you have to do, and you are happy that you want to add all 10 files. It is a lot of work to type the name of each file. So, what you can do is you can simply say git add -u. So, this will add everything that's been modified. So, changes not staged for commit, whatever files are coming here, if I do a git add, then it adds all the files. So, now let us we have simply added it. So, let us do a git commit. Okay, so I've committed that, and if I do a git log now, I can see I have 3 commits with the latest one saying printing value of square root at each iteration. Any questions? So let's see how good our script is for a range of values. So let's change the value of x to 10 to the power of 4. It's 10,000. So the answer should be 100. So let's save it and run it in the IPython shell. So now you see that it's not converged to exactly 100 in the 10 iterations. Although it's very close, but I still see that there are some digits which are non-zero. That's because 10 iterations are not enough. So what we see is that the number of iterations. In fact, if I increase this further to 1 million and save it and run it again. So now it's not even close. I mean, it has to be 1000, but it's 1296 by the end of 10 iterations. Okay, so what we are seeing here is that it needs more iterations, because what you're doing is, I mean, if you look at the function, it's going to intersect the s axis at s equal to 1000, but you start with the initial guess of 1. So it will need a lot of iterations to reach that root. So there are two solutions. One is to change the initial guess, but then for that you need to know or you need to modify that code every time, or the other is you add more iterations. So what I can do is I can have a variable k max, set it to, let's say, 100, and then I say that you run it for k max iterations. So let's run this now. Let's clear it. So now it runs for 100 iterations and it has converged to 1000. We can see that. But then it just wastes a lot of effort, because it had reached the value of s equal to 1000 by 15 iterations. So from 15 to 100, so 84 iterations simply were a waste of effort. So we need some sort of a smart method, some sort of a convergence test, so to say, so that we can figure out that the code can figure out, keep checking whether it has converged. If it has converged, then there is no point continuing the iterations. So let's add a convergence test in this case. So the way we do a test is by checking what is the change in the value of s after an update, because that's what we see, that between 86 and 87 the iteration there is no change, so it has converged. So what we will do is we will do a difference between the value of s from one iteration and one before that, and then use that for testing. So we will say that if delta s is less than some small number, let us call it tolerance, and we will set this tolerance to, let us say 1.0 into 10 to the power of minus 14. It is a very small number, but for delta s we have to define a delta s. Okay, so what I have done is I have stored the value of S before the update in S naught, and once I have done the update, once I have modified the value of S, I have defined a delta S, which is difference between S and S naught. So this helps me define a delta S, and then I can use this delta S to check if this delta S is less than tolerance. If it is, then I will say break. So break means you just come out of the loop, you break the loop. So this because this if statement is inside this loop, for loop, so if this condition is met, then it will break out of this. So let's save it and try it out this again, try it out this time. Let us print the delta S value. Okay, yeah. So you see that this delta S, I should be checking for the magnitude of delta S, not just delta S, because if it becomes negative, it's still smaller than tolerance. So what I meant was that the difference in the magnitude, so I should actually use the absolute value. So all it matters is in the Newton's method how far I am from the root. It does not matter if I am on the left or the right. It is the distance between the it's a distance between two guesses that matters. So I should be checking for absolute value. Okay, so this time if I run the code, it keeps checking the value of delta S, and delta S we can see is decreasing. So from minus 1870 it becomes minus 824 and so on, and it is negative because we start with S equal to 1 and we have to reach S equal to 1000. So it is going to the right. No, I think it's no, it's negative because we have reached too far to the right. So it's gone to 15,000, then it comes to 7,000. So it's coming to the left. So that's the reason it is negative. And by the end of 15th iteration, as we saw earlier, that it converges, so it stops. So this time it does not run for a total of k max iterations, it just stops before that. Is that clear? Any questions? I am happy to answer the questions if you have. Is the idea of this convergence test clear? For those who have done numerical methods will understand what this means. If not, then we can discuss later during the practice session. In fact, I would want to make one more change to the code. Typically, we do not check for just the value of delta S, we check for a relative change with respect to some initial value of how big the number is. So we have to, it's good to check for delta S divided by X. Okay. So if the X is very small, then delta of S would also be small. So we should always be checking in relations to X, relative error is what we should be checking, which is a better measure for convergence. Because if you start with a number which is almost close to 10 to the minus 14, then what happens is that although it's changing in a small amount, but that amount matters because you already have a very small number. Okay. So let's check this one more time. I don't need this print of delta s, so I'll just delete this. You can keep it if you want. Much cleaner this time, so you can see that by 14 iterations it converges. Let's play around with the value of x. Let's make it small. So 0.0001. Let's see if it works for small numbers. Yeah, so it also works for small numbers. I have the same initial guess, s equal to 1.0, but it works for small number as well. So let's now that we are happy with this version of the code, let's commit it. So for those who are still typing, I'll just keep it as a separate code here. Open another window. So it says modified this file, so let's add it. It also shows a SWP file, which is because I have opened it in Vim editor, so it keeps another file to store the value. So once I close this editor on the left hand side, this SWP file will vanish. It's a hidden file, it starts with a dot. So I don't need to worry about it, I don't need to add it to my repository, I only need to add the mysquareroot.py file. So once I have added that, I can do a git commit with some sensible message. Okay, so if I do a git log now, I have a total of 4 commits that are available till now. So let's play around with the formatting in the code. So if I go back to the code, in fact if I go back to the results, I see that towards the end it only gives me 1 or just 2 digits of precision. So I want to have some control over how many digits are printed on the screen. So for that, whenever I am printing, I can use the fixed point format. So when I am printing the value of s, the square root, I can simply say that this should be a fixed point format with 20 digits that are printed. Let's make it full screen for now. And there should be 15 digits after the decimal place. So remember the fixed point format that we discussed. So it will have 20 digits with 15 digits after the decimal, and there is an F for fixed point format. The same thing I will do for the final printing as well. 20.15 followed by an F. So let's save it. So now if I run it, you can see that it's printing in this fixed point format. Even the last value, it has the same number of digits, which is 20 with 15 digits after the decimal. So that gives me some control over because if you're printing things, numbers which are of different sizes, it's difficult to compare them even visually. So it's good to have some fixed point formatting when printing numbers on the screen or file. Okay, is that clear? Now I've been running this code in IPython, but I can also run it from the terminal directly. Okay, so if I just let's go to this one. So I'm in the folder where I have this code. So I can type this command python followed by my square root.py, except that I have to enable the virtual environment here as well. So for that I'll do a control R and look for the command source, and I can see that this is the command I want. Press enter. So now you can see the environment is enabled. I can go up and type this python my square root.py, and you can see that the code runs. Let's make it full screen. Let's do a clear and run it again. Okay. So I don't need to open IPython. IPython is just for playing around, testing, trying out commands. But once you're happy, you can just run the code, the Python script from the terminal, Unix terminal directly. Is that clear? Okay, so in a couple of minutes what I will do is whatever commands I have typed, I will quickly do a history, copy them and save them in Google Drive so that you can see those commands and you can play around for a couple of minutes. Okay, before that I just want to do one more thing, which is to develop a function, because you see that right now the version that we have, it works fine, but it does not work like the square root function that we have in math or numpy. So let's look at the math or numpy version of square root. So let's close this. So if well, sorry, I should be looking here in IPython. So in IPython, if I type sqrt, it says it's a function. So I can pass an argument to a function, let's say 2.0, and it prints the value. It returns a value. So I would want something similar to this. Right now the kind of code I have is, inside my script I have the value of x available, but I have to go open the script, change the value of x. So I would want to convert this script that I have to a function now. Okay. So this time I'll open it in Featherpad. So this opens my code here. So this time to make this a function, I'll have to in Python there's a we have to define a function. Let's call it sqrt2, just to be to look different from the sqrt function that we have in NumPy, and it takes as an argument x. So I don't need to supply the value of x anymore, because x will be supplied to the function while I am calling this function. Okay. And then whatever is inside the function has to be shifted to the right, so that now this function, everything that is that has been shifted to the right is a part of this function now. As we discussed earlier, that commenting, this indenting in Python actually is functional. So let's do a control S and save it. So the reason I opened Featherpad was because I could select all the lines and press a tab, and it moves them to the right. So if I want to bring them back and I can use a shift tab, it brings them back. Okay, so I have quickly converted this to a function. So let's close this now, because I have already saved that. In fact, I can open it here just to have a look at it. So this is how my file looks. So let's go back to IPython, clear it and run it again. Seems to be some error. So there is some issue with the tabs and spaces being used for indentation. So let's open it in Featherpad again. right. I think now it is okay. So I think the problem is because some editors will convert tab to spaces, okay, and some will keep it as a tab character. So that seems to be a problem. Let's try it again. Let's try running it again. So it says inconsistent use of tabs and spaces in indentation. So either you keep it tab only or in spaces only. But when I had used the copy paste, I think from or in the Vim editor, it was replacing tab with actual spaces. So what I'll do here is I'll convert all tabs to tabs. So if I go back and forward, I can see whether it's a space or a tab. So here it is a space. So if I go back, just add a tab. So every editor allows you to have a control over these things, but no, just as a quick thing, a quick fix, I am doing it. But if you're and the problem is there because I'm using multiple editors. If you use just one, things should be okay. So I've saved it now. Hopefully it should work this time. It works. Okay. So you can see that the error message is also quite helpful. So it's worth reading it and trying to understand what it means. So let's close this code. So it runs. I mean, no error, but it did not print anything. The reason is because we have simply defined a function. We have not even called it. So that's the reason it's not done anything, because we have to call the function. So let's type sqrt2 and see what happens. It says it's a function. So it has the function sqrt2 available in the namespace. That's the reason it could identify the functions. If I call it with 2.0, so now you can see it runs. It does what I expect it to do. It runs that function, and in the function you can see we are printing these messages. So it prints all these messages. All right. And just the way we were importing sqrt from math or numpy, we can also import that from this file. So I can say import or from my sqrt, import sqrt 2, sorry, not 3, 2. So it works. So what it does is so my sqrt, which was simply a file. In fact, the modules in Python are simply files which contain some code in it. So my sqrt.py was also a file. So it looked for a function called sqrt2 in my sqrt and imported that. So now sqrt2 is available as a function. So there are different ways. I mean, I can import my sqrt completely. So whatever is in there, whatever is there in my sqrt gets imported into the namespace, just the way we were importing numpy earlier. Okay, so if let's say I want to compare these functions, let's say numpy also has an sqrt function, so I can import so from numpy, so this sqrt function is now available, which is imported from numpy, and I have an sqrt2 function which is available from. So I can now compare these functions if I want, okay, the results of these functions. So let's commit this version, and then we'll stop for a break, and then we'll give you 10 minutes to practice things. So I'll upload during the break. I'll upload the history of both the terminal as well as IPython shell. So even in IPython I can type history and it prints all the history. Okay, so I can copy these into a file, upload that on Google Drive, so you can in a Google Doc, and you can just have a look at these commands. So let's commit this. So I'll do a git status. So these files such as PyCache, and you'll see sometimes PYC files being generated. So they are not required. They are just generated by the Python interpreter for some purposes. So you can ignore them, and in a while we'll see that you can ask Git to explicitly ignore these files. So it won't keep asking you to commit these in the future. Okay. So for now I just need to add. I can do a git add -u, and now if I do a git status, it says that mysqrt.py has been it's ready to be committed. So -u will only add the files which were tracked earlier. It won't add new files. So this PyCache was untracked. Okay, so -u simply adds the files which were tracked earlier. So once I have this is, I can just git commit with a sensible message. So if I do a git log now, I can see that my latest commit is available here. So before we close, I would want to push it, right? Remember that for you to see these, you have to pull it from GitHub. So I'll do a git push this time. There seems to be some problem here. Could be a network issue. So let me see what the issue is.